All right, the next two centers we're going to talk about for our triangle points of concurrency are the circumcenter and the incenter. So the circumcenter is where the perpendicular bisectors are concurrent. And so a perpendicular bisector is a line, and actually let me go ahead and draw this triangle not quite centered like that. I'm gonna draw the vertex a little bit off-centered so that you can see this better. Perpendicular bisector. It bisects the side that it goes through, so we're going to kind of draw this like cutting this side in half, and it's perpendicular. So these two pieces are the same length, and then it's perpendicular to that side. All right, so a perpendicular bisector is perpendicular to the side and it bisects the side. All right, perpendicular bisector is perpendicular to the side and cuts the side in half. Perpendicular to the side, and cuts the side in half. All right. Interesting note about this is the circumcenter is also the center of the circle that can be circumscribed. Circumscribed. About the circle. So what you'll notice is in all three of these pictures, we have three different scenarios. Circumscribed means that if you start with the circumcenter, you can take this and you can actually draw a circle around that triangle, and what happens is if you use the circumcenter as the center of the triangle and use the distance from the circumcenter to the vertex as the radius, you can actually draw a circle, and that triangle will be inside of the circle. So that circle is circumscribed around the triangle. All right, so the vertices are equidistant from the circumcenter, and this is the very mathy part that's going to end up showing up in our problems on our worksheet, that the distance from here to here is the same as the distance from here to here is the same as the distance from here to here. The distance from here to here is the same, the distance from here to here, the distance from here to here. It's something that is subtle and it's easy to not notice. Okay, so the vertices are equidistant from the circumcenter. I would say if you've got a marker or a highlighter handy, I would maybe even highlight that. I had to pause my video so I could find a marker that would maybe work as a highlighter. This might be too dark. Oh no, that's pretty good. There's my highlighter. Okay, the vertices are equidistant from the circumcenter. They're actually the radius of the circle. That is circumscribed. Okay. Or the distance is the radius anyway. The distance from the circumcenter to vertex is the radius. Okay, so the distance from the circumcenter to the vertex is the radius of that. So this right here. That's what actually helps me to remember it. All right, so that's really important. That's going to show up in math problems. All right, another interesting note is that I was going to write it again, but it's actually on the sheet. The circumcenter doesn't have to be inside the triangle. So this is interesting, just like the orthocenter, is that the circumcenter is a center of a triangle that can be outside the triangle. So that's interesting. In a right triangle, the circumcenter can show up on the hypotenuse. All right, in a right triangle, the circumcenter can show up on the hypotenuse. So that's something that's pretty interesting. All right, Leonard Euler. I know it looks like Euler, but that's not how you pronounce it. You pronounce it Euler. He's a mathematician. He noticed a relationship between the three classical triangle centers. Those are the three that we've just studied. They are collinear. That means they're in a straight line. The centroid is always in the middle of the other two, and the distance between the centroid and the orthocenter is always twice as much as the centroid and the circumcenter. The line that these three centers of triangles lie on has been dubbed the Euler line. So that's just kind of an interesting piece of information. I could probably come up with some math problems to do that, but it's not something that they commonly test you on, so I did not do any math problems with this, but I did think it was worth mentioning. All right, the rest of our notes. This is not a classical triangle center, but we're going to study it anyway, called the incenter. So the fourth center of a triangle that we're going to study is the incenter. This is where the angle bisectors are concurrent. This is where the angle bisectors are concurrent. And as you can imagine, an angle bisector is the line that cuts an angle in half. All right, so this is the line that cuts an angle in half, right? The incenter is also the center of the circle that can be inscribed in a triangle. So you'll notice this is interesting because if you take the incenter, you can actually find the point where the angle, so this is the part where it bisects the angle, and then this is the part where the angle bisector touches the opposite side. So if you measure these are actually the radius of that inscribed circle. You can actually draw and you can inscribe a circle. So the sides of the triangle are equidistant from the incenter, and we're going to go ahead and highlight that as well because they are the radius of that inscribed circle. We're going to write there the radius, or the distance is the radius. I'm going to be a little bit more specific this time. The distance is the radius of that inscribed circle. So whenever you look at this, not the angle bisector itself, we always know, so that's where we can find some of our math problems, right, is that we always know that these angles are going to be bisected, so this angle and this angle are going to be the same, this angle and this angle are the same, this angle and this angle are the same. But the interesting thing is that when you look at where the angle bisector hits the other side, this short little line right here, this short little line right here, this short little line right here, those are all going to be the same length. So we can say this is the same, this is the same, this is the same. This is the same, this is the same, this is the same, because they're all of radius for that inscribed circle, all right? Because of this, because this works, we have this inscribed circle in all of these. Another note, we didn't explicitly state it in these notes, kind of like I didn't explicitly state it with the centroid, but it made sense for it to be true. The incenter is always inside the triangle. All right, so tomorrow when we work on our practice, we're going to focus on kind of the mathy things, but it is going to come up on an assignment where we're going to focus on maybe some of these facts that show up on these notes of which triangle center is inside the triangle, which triangle center could be outside the triangle, which triangle centers have to do with circles, things like that. So there are some facts that we're going to want to know about these triangles so that we can identify which center is which.